So today we're talking about deterministic policy gradient algorithms. This is a topic within reinforcement learning. And the first thing we're going to be discussing with respect to this topic is the distinction between deterministic and stochastic policies. So we consider the following scenario to get some clarity in this. We're in a car, or we're driving a car automatically with some sort of policy. The policy is what dictates the decisions that we make, and it bases those decisions on the state that we're in. So the state in this case would be where the car is. So in a Y junction, as we can see, there's a sign indicating that we are at the junction, and then we can turn either left or right. A deterministic policy always selects the same action given a certain state S. So the state would be where we are, as I said. And for a deterministic policy, we would always act the same way when we're faced with that state. So in this scenario, we might, for example, turn right, as is indicated by my arrow in the figure. We would always turn right when we end up in this scenario, regardless of if we do it one time or a million times. And this is just a deterministic policy that we follow. In contrast to this, a stochastic policy may select different actions while faced with the same state twice. So here, for example, we might have a 40% chance of turning right and a 60% chance of turning left. So if we're faced with this scenario 1,000 times, 400 would be one way and 600 would be the other way. So in this way, it's deterministic. So we can't say a priori which direction we will take in this juncture. The paper that we're going to be focusing on is called deterministic policy gradient algorithms. So we're going to be focusing on the deterministic policies for this paper. Okay. Before we get into any theory, we want to first define what we're trying to do in a reinforcement learning setting to begin with. When we're sort of acting in the environment, what we're trying to do is maximize the amount of rewards that we're getting. And one way to quantify this is through the performance objective. That's what it's called. In order to get a sense of how this is defined, we're first going to look at something called the improper discounted state distribution. That's indicated by the rho that we can see here in the equation. And if we have a closer look at the terms here, we're going to start dissecting it by looking at the rightmost term. So this is the density at state S prime after transitioning for t time steps from state S. So imagine starting in state S and you want to make it to S prime, and you have t steps to do so. You need to do it in exactly t steps. So there's no like you can do it in 3 steps if t is 4. It needs to be exactly t steps. P of this is then the density or the probability of ending up in state S prime after taking those t steps. The term just before P1 of S is the probability of being or starting in state S. Gamma to the t minus 1 is a discount factor. And the reason this is here is because if you take lots of steps to get to a certain position, it's kind of far away in the future and we don't care about it as much. So gamma will be a number smaller than 1, and as t gets really big, this term will grow smaller and smaller or shrink. And if we zoom out a bit, we see that we have a sum here ranging from t equals 1 to infinity. So basically what we're doing is we're considering the probability of starting in the state S. And then for the state S prime, which we want to go to, we vary the amount of steps that we can take to get there. And then we sum up the probabilities. But we don't sum them equally. We sum the ones that come early with a higher weight than the ones that come close to infinity amount of times. The last thing we need to do is integrate over all the s's. So in the expression here, we can see that we have rho of S prime on the left-hand side. And so we don't want to have an S in the right-hand side. What we do is we integrate over S to take into account the probability of starting in either of these states. And the result that we get then, rho of S prime, is a metric that tells us how likely we are to be at S prime sometime in the future. It's sort of an average metric of all the future that we have to expect in front of us. Based on this, we can then take the step to define the performance objective. And what the performance objective is, as I said, sort of the cumulative expected reward that we will get in the future. So if we consider the expression to the right-hand side, we can see that R of SA is the reward for being in state S and performing action A. And then we have a second part of this equation here, which tells us how likely we are to be in state S and perform action A. So rho of S as we said just before, tells us how likely we are to be at S in general in the future. And then pi of SA tells us the probability of acting according to action A, given that we are in state S. So this blue part in total tells us how likely we are to be in state S and perform action A. And then we integrate this over all states and actions. And that's when we get the performance objective. So it tells us how much reward we expect to get in total for all the future going forward if we discount the rewards. So the higher the performance objective, obviously, the better we're doing. And that's the good thing. So we want to maximize this. And this can also be written as an expectation, which is what we see below. And the goal then in reinforcement learning is to obtain a policy which maximizes the cumulative discounted reward from the start state. And that is exactly the performance objective. Okay, cool. So next thing then, how do we optimize this? We know that we want to maximize this performance objective, but how do we do it? Normally, when you try to maximize a function, you would follow gradient ascent or gradient descent, and we would do that here as well. So we would take the gradient of the performance objective, and after performing some calculations on the expression that we had in the last slide, this is what we're essentially going to end up with. So notably enough, the row term that was existent here actually is maintained. This isn't far from trivial because the policy pi here that row depends on itself depends on the parameters theta that we're taking the gradient with respect to. So it ends up being this way that the row is unaffected, let's say, or that it comes out the same way after the derivation. But that is really not something to take for granted. And then in addition to this, we then have the gradient of the policy here on the right-hand side, and the reward turns into a Q function after differentiation. This can also be written as an expression similar to what we did before. And this is a really powerful statement because we reduce the computation of the performance gradient to a single expectation. And the good thing about expectations is that you can estimate them, for example, with Monte Carlo. So if you generate a bunch of sequences of the expression here in the brackets, the average of that is simply going to be the expectation. So we have a very natural way of evaluating it. The problem, though, is that you need to be able to evaluate this in the first place, which is in here. So most algorithms must estimate the value function Q. Okay, so if we look at the stochastic actor-critic algorithms, so actor-critic is a topic within reinforcement learning. We won't go into that much detail, but the actor adjusts the parameters theta of the stochastic policy by stochastic gradient descent. So we update the thetas in order to improve the policy that we get, and we do that with stochastic gradient descent of the performance objective. So the performance objective was the J that we just looked at. The job of the critic is then to estimate the action value function, and this is not the true action value function, but an estimate of it, a parameterized estimate. So Q with parameter vector W of SA is an approximation of the true Q value function that we have for the policy pi. And because we make an approximation here, there's normally a bias associated with this. So Q won't be a perfect reflection of Q pi, of course. There will, however, not be a bias in the estimate if the following two conditions are true. So the first one basically tells us that Q pi of SA needs to be the gradient with respect to theta of this expression here. And if we write this out, so an equivalent way of writing it, which makes it a bit more comprehensible, is you take the derivative with all different like theta dimensions that we have. So d d theta 1 all the way to d theta n of the same expression here, then times the w vectors of the associated dimension as well. And what we see here is that the Q function must be linear in the features of the gradient log. So these terms here, W1 to Wn, they're all linear. So you could think of them as constants, and then we have these features that it needs to be linear in. So there can't be any other relationship there. Moreover, the W's must minimize this equation that we have here, which is the mean squared error under the relevant expectation. And if you were to keep these two conditions, or if you were to follow these two conditions, you would get something that's not biased. And that sounds like a very good thing because, you know, a bias towards a variable that you're trying to approximate is not necessarily a good thing, or is generally a bad thing. However, it's kind of a surprising result because it does not improve over the reinforce algorithm if you do this. And the reinforce algorithm is a much simpler algorithm that doesn't even use the same framework. So normally this second criteria is relaxed in favor of policy evaluation algorithms. And so just because we have a bias doesn't mean necessarily that we're doing poor approximations of the quantity that we're trying to approximate. Okay, so another thing, in off policy after Critic. So off policy is when you follow a policy that's not the same as the one you're trying to approximate. So then we would sample a policy gradient from a behavior policy. And then it's quite common practice to model the performance objective as the following. So you would have rho of some beta, which is the policy that you're following now then, so the behavior policy. And then the value function v according to the policy pi of SDS. This can then be extracted as, you know, a second integral. So the value function would be the integral over S and A, or well, the integral over A for the policy pi times the Q value. There should be a dA here as well that was neglected, but nevertheless, I think you get the idea. The off-policy gradient then becomes the following expression. So we're differentiating again, taking the gradient with respect to theta of this expression, and but we're following B or beta for the performance, and that, you know, has an effect on the performance objective. After differentiation, we arrive at this expression here, and this can also be written in an expectation form. So the details of these calculations we won't really dig into the depth of, but it changes slightly when you're following another, well, behavior policy that is not the same as the one you try to approximate. Okay, so putting this in an algorithm, an off-policy actor critic algorithm uses behavioral policy beta to generate trajectories. So these are the explorations that we do in our environment. The critic estimates the value function v, big V of small v of S, which is an approximation of the value function according to the policy that we're interested in. And it does so from the sample trajectories, you know, that beta generates, or and then with gradient TD learning, so temporal difference learning. The actor then updates the policy parameters by stochastic gradient ascent of the expression, and this again is something that we saw before. However, the Q function here is normally approximated by delta, which is the return at the next time step plus the discounted value function of the next time step. So this is, you know, the reward that you would get in the consecutive time step. This is how good the next state is if you discount sort of the future, like if you discount the time step that you need to project. And then you remove the current value of the state. So this difference here, if we neglect the discount on the second one here, kind of tells us how much better this state is in comparison to this. And this then, the reward, takes into account basically what we get in this time step that we're considering. So these two together are kind of how good our prospects are for the future. And this is kind of what we have now. So if our prospects for the immediate or for the future are better than the value of the state we're in now, this would be something positive. Otherwise, it would be something negative. And lastly, an important sampling ratio is also taken into account to adjust for the discrepancy in behavioral and trained policy. So this is something you need to add because you're not following the same policy as you're trying to evaluate.